assign our priorities, all that fun stuff, reorient the molecule, all that jazz to make sure everything aligns up perfectly. Whoops, I did not mean to do that. So let's take a look at that first one. I'm going to pick this as my chiral atom, that little red dot. So I want to identify the 4 different things around that. And at the same time, so if we're trying to find a chiral atom, while we're looking for that chiral atom, we can identify if it has 4 different things around it. Okay? And while we're doing that, we can assign priorities. Okay? So number 1, I'll add a hydrogen, because I know that carbon needs that extra bond. Okay? And I know that because it's not charged. If it was a charged carbon, then I'd evaluate a slightly different situation. As far as distinguishing, at that carbon, what I now need to do is look at the 4 things that are attached to it and assign priorities to those 4 things. Which of those 4 things stands out the most to you?
The carbon bonded to the chlorine.
Okay, so if we look at the chlorine, okay, the chlorine has the highest atomic mass of those. We're looking at chlorine to hydrogen to carbon. Chlorine absolutely has the highest atomic mass, so I can assign a 1 to the chlorine. What else stands out?
The carbon bond hydrogens.
Okay, our hydrogen is probably easier to identify. I'll just heard what you said. Give me a second. Okay, you mentioned something about the carbon bonded to the other chlorine. I'm not sure what you mean by that. Can you go through and elaborate?
The other 2 are both going to be the carbon-to-carbon bonds, but the one that's bonded to the chlorine is going to take priority.
Okay. So what you're looking at is evaluating the difference between those last 2 carbons that I've got highlighted with that blue X. Okay. I would argue I don't want to look at that quite yet. The hydrogen was easier to evaluate, so I dropped the 4 on the hydrogen. And then at this point in the game, I might panic and say, I'm going to get confused. I don't want to worry about this. I'm going to move on to another question in the exam and come back to it later. When I come back to it, half the question's now solved for me. It's a little bit easier of a question to deal with. Okay? So what we're comparing then is the carbon on the left to the carbon on the right. So remember, when we go through and deal with priorities, it's only the atom that's immediately attached. And if we go through and look at that, carbon and carbon, there is no difference as far as the atomic mass goes. So what we then do is move to the next highest priority atom out from that position to see if there's a difference. Right? So one option to see if there's a difference before we even evaluate anything else is to kind of cut the molecule in half. This was something that I believe Lee was suggesting, the textbook mentioned, is if we cut immediately in half, can I tell a difference between those 2 halves? Yes. That means those carbons are different from each other, which means the priorities will be different from each other. Right? Which means I do have a chiral atom. I now have to define whether it's R and S. So now we can go back and say, okay, which of those carbons has higher priority? Well, again, carbon, no difference. So what we'll do is we'll advance from that carbon to the next highest priority atom. Okay? From our leftmost carbon, what's our next highest priority atom? It's a carbon. From our other carbon, what's our next highest priority atom? Chlorine. Chlorine versus carbon. Which has higher priority? Chlorine. So chlorine has the higher priority than carbon, which then means what about these 2 carbons? The carbon with the chlorine gets 2. The other one gets 3. Now that my priorities are set up, I need to make sure that the molecule is oriented in such a fashion that I can actually assign R and S. To do that, the lowest priority atom must be aimed away from me. Where is the lowest priority atom right now? It's aimed away. Okay, go figure. You asked me to pick a simple one, I pick an easy one. Okay, so we go through and we now connect 1 to 2. Let me clean some of that up. That looks really messy. We can now connect 1 to 2, 2 to 3. Which direction are we turning? Clockwise, which means that carbon is now what orientation? R. Okay? For sake of clarification, let's go through and number that carbon. What carbon would we number that? Really doesn't really matter as long as you call it 1 or 2. I'll accept either of those. Since it's the first one we did, let's go ahead and call it 1R. Okay. And I'm going to attempt, we'll see if I can layer on top of this. We'll see what happens. Okay. The next thing I'll go through and do is see if I have a different chiral atom. So I can move out to, say, that purple carbon. Is it a chiral atom? How do you know that? If we draw in the other atoms, we have 2 hydrogens. Are those hydrogens chemically different? No. Which means that atom is not a chiral atom. So I would continue to go around my structure to see if I can find a chiral atom. I should eventually get to this carbon as being a potential chiral atom. Okay, we're missing the hydrogen, so I'll go ahead and show that hydrogen. What other information should I add about that hydrogen? It's wedged. Okay. And I now go through and do the exact same thing I did with the previous one, except I'm going to do it faster now. Chlorine's 1, hydrogen is 4. We now compare between those other 2 carbons. This carbon becomes 2, this one becomes 3. Okay. Remember, before we decide clockwise or counterclockwise, what do we have to do? Orient so the lowest priority is aimed away from us. Our lowest priority is aimed at us. So depending on your comfort level with this, what you should do is actually reorient the molecule. There are 2 ways to do that. One, you have a model kit. Right? That does not mean building the entire structure. What does it mean building? Just a chiral carbon. And within that, you can go through and put a white ball, no ball, a red ball, and a blue ball on that. And then you can go through and label your 1, 2, 3, 4 according to those different colors. Wasn't that funny? Okay. Once you've got it labeled, then it's just a question of picking it up and moving it to a different orientation so the lowest priority is physically aimed away from you, and then just connecting 1 to 2 to 3. Okay? Off of the model. You now have your answer. Okay? The other option is literally flipping the structure and redrawing it. Okay? Not my favorite method. Well, kind of not my favorite method. When I was in OChem and trying to deal with this, I would always draw these out because I could never consistently get it correct. If you talk to other people, they'll say, oh, you can flip, you can rotate, you just change it, and they can come up with it and do it consistently right. I can't. Okay? I had to go through and draw it. So what I'm going to do is take the structure and flip it over. When I flip it over, I will have my hydrogen here, my chlorine here. The other position, I'll have my chlorine and my other hydrogen. So if we color in, there's my red, here's my purple. What happened with the hydrogen as I did that flip? It's now dashed going away. What happens with the chlorine? It's wedged coming at me. I can now transfer over all of my priorities. 1, not a 2, that's a 4. 2, 3. Which direction are we turning? Counterclockwise, which means that's clockwise. Sorry, clockwise, which is R. I can now go back to my name, and I have 1R, 2R, and I finish out the rest of my name. Okay. As some of you may notice, give me a sec. If we went through and looked at how we assigned in the previous case and just connected 1 to 2, 2 to 3 in our purple, that was going counterclockwise, which is S. By flipping the structure over, all we did was just switch our viewpoint from R to S. So if you see the hydrogen aimed at you, go through and run the whole protocols as normal, but then just change it. Okay? That S needs to be shifted to an R because you're looking at it backwards. Okay? That is the only version of these kind of manipulations that I can deal with. If the lowest priority is not wedged or dashed, but in the plane of the paper, I personally hate that question. I have to go through and redraw the structure. Okay? I have to do the rotation. That is me personally. Okay? Feel free to talk to different tutors, check out online. I've noticed lots of people have suggested there's other methods to doing it. I cannot get those other methods to consistently work. Okay? With two hands, 1, 2.
Can you just write it as 1, 2R, or do you actually have to write 1R, 2R?
You have to write 1R, 2R. You have to delineate each of those chiral atoms. Okay? Oh, okay. Other questions with RNS? Okay. I am just going to mention this briefly. I'm not going to talk about it now, but if we go back like a whole bunch of different slides. Talked about all these calculations involving optical activity. I'm going to post a supplemental video where I go through and solve this problem. At most, you'll see one question like this on this exam, and you will never see it again, okay? Which is why I don't want to spend any time on it in class. So it's up to you if you want to actually spend the time to watch that video and understand what's going on with it. The question that you will see is something like this. Okay? Which of the following show optical activity? Okay. A, R enantiomer. Should we see optical activity? Okay. R means that I have a chiral molecule, and I only have one version of the chiral molecule. I do not have its mirror image. Do I see optical activity? Yes. The plane of polarized light comes in, sees that R molecule, and it rotates some direction. We don't know whether it's positive or negative, but it will rotate. Since it never encounters an S molecule, it will only continue to rotate that same direction. Okay, as it encounters more R molecules, and we see more rotation of our sample. So that first sample does show optical activity. I guess we could use a check mark. I don't know. A meso compound. Okay, that's a little bit trickier. If we take a meso compound, we get something along these lines. I'll give you 30 seconds, maybe a minute. Assign R and S to your two chiral atoms for the meso compound. And I intentionally gave you one that should be easier to solve. Did you guys solve it yet? No? Okay, take a little more time. All right, that's all the time I'm giving you. Red carbon has what chirality? R. Blue carbon, S. Half of the molecule is R, half of the molecule is S, and they are identical, R and S. So we have effectively an enantiomer within the molecule. Kind of a bit weird. Okay? What is that going to do as far as the optical activity? Our light comes in, sees the R, rotates one direction. Which direction do you want it to rotate? Clockwise, which is this way, right? Okay. Now it comes in and sees the other half of the molecule, which is S. Which way does the light rotate? The opposite direction, in an equal magnitude. Why is it equal magnitude? Because it's not just the same molecule, it's the same type of chiral arrangement, the same atoms arranged around your chiral center. Okay. So it will rotate it back the exact same. Which means what is the net result when we look at the optical activity? 0. There is no optical activity for a meso compound. Yes?
But if that chlorine was away from you, wouldn't it just B1R, 2R?
If the chlorine was, one of those chlorines was aimed away from you, then your chirality changes and you don't have R and S, you have S and S, or R and R. Will you see optical activity then? Yes. Okay. And in that case, you won't have a meso compound. This is a meso compound. One of your characteristics of a meso compound, you have to have two chiral atoms. Why do you have to have two? At least two? One is R and the other is S. Every meso compound will follow that rule. Right? What happens if we have a mixture of enantiomers? 1 to 3. So one part of our solution has the S enantiomer, the other one, or the other 3 parts are R. Should we have optical activity? Yes. What's our optical activity going to be due to, primarily in this case? The R. Why? There's 3 parts of the R, so we absolutely see optical activity in this case. What if we have another mixture of enantiomers, but now it's a 1-to-1 mixture? Okay, no, that's effectively the same thing as a meso compound, except we're now looking at 2 separate molecules. A meso compound has the R and the S in the same compound. In a mixture of enantiomers, half of our molecules are R, half of them are S, so it's 2 separate compounds. But we still see the same net result. No optical activity coming out of that. That type of mixture gets another name, which you may or may not have heard of yet. So let's see, has anybody heard of it? Ends with R. Racemic. A racemic mixture is just in reference to the fact that we have a mixture of enantiomers that is 50% one, 50% the other. This is a very popular type of question to ask, because we can say 1-to-1 mixture of S and R. Does it have optical activity? No. I have a racemic mixture. Does it have optical activity? No. I have a mixture that is 50% the S enantiomer. Does it have optical activity? No. All of those are getting at the exact same point. We have a 1-to-1 mixture of the R and the S. Okay? And all of those are referring back to kind of this idea of a racemic mixture. Is it always going to be called racemic? Okay? No. Just like every verb has different conjugations, racemic has all sorts of different conjugations as well. The other common one that I've heard is racemate. Okay? Same thing. Okay? Last one, a mixture that has 0% enantiomeric excess. Well, that already says no up there. 0% enantiomeric excess, what does that mean? It's another way of saying it's a racemic mixture. I have a 50-50 relationship. How did you calculate the enantiomeric excess? I know we did this one fast. Okay, the enantiomeric excess was 1 minus the other. How do you get 0? R has to be equal to S. We have the exact same amount of each of those. Okay? Very popular question to show up on your ACS exam. Okay? Also a very easy one to ask on any exam because it gets at looking at assigning R and S for all these different things. We could give you a structure and say, is this compound optically active? Okay, so optical activity is a big concept as far as just evaluating, do you have a chiral atom or not? Okay? So that one, just to make sure we got it on there, was a no. Questions? Now what we're going to do is move into what I would argue is my favorite part of organic chemistry, but it tends to be everybody's least favorite because nobody wants to spend the time to learn it, okay, which is fine. I mean, that is the way it is, but that's ultimately what's happening with this. This is chapter, 15 and 16? Yeah. Okay, chapter 15 and 16 in your textbook. They've actually divided it up slightly different than most textbooks I've worked with. Chapter 15 looks at ultraviolet spectroscopy and infrared spectroscopy, which is actually a better grouping than other textbooks. And then 16 looks at actually NMR first, then mass spec. Okay. I've got them kind of organized on how I would look at them, with the most important one being the one at the bottom. NMR is by far the most valuable form of spectroscopy that we've got. Okay, both ultraviolet and IR deal with the electromagnetic spectrum. Mass spec, literally you take your molecule and you blow it up into a ton of tiny pieces, and then you look at all the tiny pieces. Okay? NMR, you're looking at the magnetic characteristics of atoms, okay, actually in nuclei. Okay, so those are our four main categories. We have subdivisions within these. You should become proficient at solving spectra as quickly as you can. Okay? Timelines for this is it takes a lot of time to actually be able to master these techniques very quickly. Okay? But one of the things that's really nice about spectroscopy is that if you're given a sequence of spectra, you are also given the answer. Okay? The answer is buried within the spectra. You have to be able to interpret the spectra, but like no other question, okay, you have the answer there. Okay? All you have to do is rearrange those pieces and interpret them to get to the answer. Okay? As an extra added bonus when it comes to spectroscopy, think to your final, and most of all of your exams are made up of multiple choice. So not only do you have the answer given to you in the spectra itself, but you also have the literal answer right underneath the spectra. So one of the very common techniques to use when dealing with spectroscopy on the exam is process of elimination. Eliminate things that do not make sense. Okay? Super, super helpful. Okay? Find the things that fail. It will help. So, electromagnetic spectrum, different ranges within our spectrum do different things. Okay? The characteristic ones that we're going to look at would be the IR range, which includes molecular vibrations. So if we hit a molecule with IR light, it vibrates. Okay? You heard of infrared heating? Yeah, we've got a lot of grills with infrared heating, fancy stuff. Right? What are you doing? You're hitting it with IR light, causing the molecule to vibrate. Well, if you all start vibrating right now in your chair, you're all going to get really, really hot. Okay? Same thing's kind of happening when you're looking at IR. All you're doing is causing your molecule to vibrate, and we can detect that absorption. The next section that we can look at, that we'll look at kind of briefly, would be our UV, okay, and partially our visible region. Okay, so it's typically referred to as UV Vis spectroscopy. What's happening is that in that particular energy range, that corresponds to enough energy to cause an electron to jump from a ground state to an excited state. Okay? As another form of spectroscopy, what can we do? Once we've excited it to the ground state, or to the excited state, what happens?
Falls back to the ground.
It has to fall back to the ground state. And if conditions are perfect, what do we see in that process? A photon emission. So we could look at fluorescence spectroscopy, which is the process of exciting your molecule to then watch it spit that electron back out. Okay, so we can look at different transitions and do different forms of spectroscopy within those. We won't worry about fluorescence spectroscopy, at least this semester. So UV Vis, we end up scanning through a range of wavelengths, and what we do is just look to see, did the molecule absorb that light? So it's almost always plotted as an absorbance versus wavelength. So in this case, what ends up happening is that at 700 nanometers, what happens? Nothing. The light passes directly through the sample. We get zero absorbance, which means the light did not interact at all with the molecule. But if we jump to 224 nanometers, what happens? It absorbs the light. Why did it absorb the light? We took an electron in that molecule from its ground state, and it jumped to an excited state. The energy required to do that jump corresponds to 224 nanometers. Okay? So each of our molecules will absorb light differently. Okay? And we can use the absorption spectrum to potentially identify that compound. Yes?
When you say it absorbs the light, the photon, where exactly is the photon going? Is it going into the bond? Is it taking its place?
The photon is going into an electron and causing its energy to jump. So we're taking an electron from, say, I think we'll be talking about a little bit more in depth in a second. So we'll take a look at that a little bit closer. Ultimately, you're taking an electron from one orbital and you move it to a higher orbital. That energy difference is the photon of light that was absorbed. Okay? So we're supplying energy through light, that's all light is a form of energy, to that electron so that it can jump to a higher energy orbital. We're just pushing it up there. Okay? And because we have quantized orbitals, which you talk about in 151 and 130, we only see particular jumps. It has to be the exact energy for that individual jump. Otherwise, the light passes straight through and the electron never absorbs that energy. You have to hit that perfectly, okay, within sort of boundaries. When we're looking at UV vis, one of the common methods to look at is the Beer-Lambert law, which I'm pretty sure you've seen in 152. You're looking at the relationship between absorbance and what are all those other symbols? I think someone keeps mumbling it. Maybe I'm not hearing it right. Epsilon is the extinction coefficient. B is the path length of our sample. C is the concentration of the sample. If you increase the concentration, what should happen to the absorbance of light? It should increase. So we see that direct relationship. If we increase the length of the sample, so our light has to pass through more sample before it gets detected on the other end, what's going to happen to the absorbance? It's going to increase. The extinction coefficient is the only one that's kind of weird. The extinction coefficient is characteristic for the molecule. Okay? What that's acknowledging now is how much of the light is absorbed by that individual molecule. That's kind of the way to think about it. The extinction coefficient will only be accurate for a wave, well, it's accurate at individual wavelengths. Right? And it is something that we could theoretically calculate really easily. What is the extinction coefficient for this molecule at 600 nanometers? What was that? It's 0. No light is absorbed. Your absorption is 0, hence it doesn't move off that baseline. Does it matter how long the path length is? No, no light's absorbed. Does it matter the concentration? No, no light's absorbed. Okay? Epsilon, the standard at that point, will be 0. So I can change the path length, I can change the concentration. It will have no effect on the result. Where does it become trickier to calculate the extinction coefficient? When it's not 0. Okay? And depending on what you're doing, you may go through and calculate the extinction coefficient. You may borrow it from somebody else's research. Okay? Or you may approximate it to no end. What's happening in each of these individual transitions? So what we've got on the right there is a representation of the electron orbitals for, I think this one is actually butadiene, not the compound shown. Right? Remember that whole section where we went through and looked at the molecular orbitals, molecular orbital theory? Okay, which was actually chapter 3, I think. Why did we go through and do all of that? UV vis. Okay? The whole understanding, or our whole understanding of ultraviolet spectroscopy comes back to molecular orbital theory. We're looking at individual orbital levels. Okay? And what's happening for UV vis is that our electrons are jumping from ground states, where the electrons actually naturally exist, to excited states. Why can they jump to the excited state? We're supplying energy and they're unused orbitals. They don't have any electrons in them. Okay, so depending on what orbitals we're jumping from, we'll see different energies necessary to make that jump. Okay, and it turns out for UV vis spectroscopy that most commonly what we're looking at is the jumps between these two orbitals. What is special about those two orbitals? What is unique about this bottom one?
It's the highest energy level.
It's not the highest energy level because this one above it is actually higher.
Yeah. That one's the least occupied.
okay, we have our highest energy occupied molecular orbital at the bottom, and we have at top our lowest unoccupied molecular orbital. That's an awful lot of words, so we end up translating those into HOMO and LUMO. Highest occupied molecular orbital, lowest unoccupied molecular orbital. Interesting thing to talk about as far as materials go. The electrons in our highest occupied molecular orbital are sometimes referred to as the valence band. Anything up in our LUMO is typically referred to as our conduction band. Where is that important? LEDs, solar panels. We're looking at exciting electrons between those two barriers, and we want to maintain that barrier in such a way that we can either get electric current to flow out one end, okay, in which case we're using solar cells, or what we're doing is pumping electrons in, okay, into our conduction band and hoping they recombine and jump across that gap into our HOMO to give us a light emission.
You said
Okay.
the LUMO is the,
Typically your conduction band. It's a little bit more complex than that because you've definitely got different systems, but it's pretty close to that. Okay? So molecular orbital theory actually explains a lot of the stuff that you would see in an engineering class when looking at LEDs and solar panels. Huh, funny that, organic chemistry, looking at inorganic stuff. Okay, kind of cool things. So, how do we go through and decide our orbital diagram for these? Okay. If we looked at the raw orbital diagram for this molecule, it would be a bit tedious. We've got a lot of different things going on in it. Okay. But what we're concerned about is our highest occupied molecular orbitals. What are our highest occupied molecular orbitals going to be? What type of symmetry do you think are they going to have? Or said another way, what types of bonds do we have in butadiene? We have pi bonds and we have sigma bonds. Okay. Which of those is higher in energy? Pi. Which orbitals do you think we want to look at for our orbital diagrams? Our orbitals of pi symmetry. Okay, so what do we go through and do? We look at each of the carbon atoms and we look at the p orbitals possible to it. So we've got 4 carbon atoms, which means we have 4 p orbitals. Sort of looking p orbitals. And remember, each lobe has a phase. Okay, if the phases all overlap, are we high energy or low energy? We're lower energy because that allows for the electrons to jump from one pool to the next to the next. So we could go through and shade these all in this fashion. Now we're at our lowest energy orbital. Okay, did I have to shade them in that way? Is there another way that I could possibly have shaded these so that they all overlap? Could have done the bottom, but it's ultimately the same thing, so no real difference. What if I changed how I had colored them in? Is that higher in energy or lower in energy? Why is it higher in energy? What is happening right there? There's a node. The electrons cannot exist in that space. We can't jump electrons across because our phases aren't aligned. So we have a node. What happens when we increase the number of nodes? We increase the energy. So this molecule is higher in energy. Oh, man. What happens if I had drawn it this way? Higher or lower in energy? Higher in energy. Why? 2 nodes. Is there a last option? We could have gone with 3 nodes. How many drawings did I just do? 4. How many orbitals did we start with? 4. Guess what we just drew? All of our molecular orbitals for the pi system. Okay. 2 of those are bonding, 2 of those are non-bonding. Okay? And so if we take a look at what your textbook has put together, that's what they're trying to show. And that lowest energy form, what happened? Our phases were all in alignment. Man, those are just getting worse and worse. Okay? So that our electrons can jump all the way across. What happened in the next one? Notice the phases change, and we end up increasing the number of nodes. Right? So we had these 4 molecular orbitals. Remember one of the things when we talked about chapter 3, I said, don't worry about putting in electrons yet. Guess what you got to worry about now? Putting electrons in. How many electrons are involved in the pi system for this molecule? Why are there 4? There's a pi bond, there's a pi bond. How many electrons go into a pi bond? 2, 2. I now drop those into my molecular orbital diagram. They're my bonding pi orbitals. Right? My anti-bondings are the ones then above. If I now evaluate the ground state of this molecule, I've got my electrons now in that HOMO orbital. If I provide the exact amount of energy necessary, what can happen? That electron can jump to the lowest unoccupied molecular orbital. So my drawing changes because I've now moved the electron from a ground state to an excited state. The difference in energy there corresponds to, okay, so that difference in energy happens to be somewhere in our UV range for ultraviolet light. Right? So what's happening within these is we're just using energy to excite our electrons to a higher state, and we can detect that absorption. That's all that's really happening with UV vis. We can take this further, but really all what we're going to be concerned about is what are the structural effects on that absorption. So what is almost always represented as lambda max. Why do we say lambda max and not energy? Typically when we go through and look at spectra, we're almost always looking at the color of the light. Well, the color of the light we almost always associate with a wavelength, not with energy. Are they translatable? Absolutely. They are one and the same thing. You just have to solve for them using Planck's constant, speed of light, and all that fun jazz. Okay? So what happens to our structures? So let's take a look at that top 2. Don't do that. What's happening up here? Okay, to our lambda max. And actually not that top box. As we move from ethene to butadiene, what happened to lambda max? It increased, which means what happened to the energy? What's the relationship between energy and wavelength? Inversely related. The gap between your HOMO and LUMO actually got smaller. Right? That then shifts the wavelength further into the ultraviolet range or into the visible range. Right? What's going to determine that gap between our HOMO and our LUMO? It has to do with the conjugation of the pi bonds. Right? In that first case where we only have one pi bond, our electrons can only exist right there in that intermediate space. If we move to the butadiene, we do have those pi bonds. Okay? But what makes those pi bonds different than in ethene? They're conjugated, which means resonance. That resonance does what to the gap between the HOMO and LUMO? Shrinks it. If that gap shrinks, your energy decreases, your wavelength increases, and we start to move into the ultraviolet and visible spectrum. If we conjugate in more double bonds, what happens to the wavelength? It increases even further. More double bonds. Continues to increase. Okay? So what we're looking at is, as a question could be, which of these structures is going to have the largest lambda max? Well, it's going to be the one that has the most double bonds. Okay? And in particular, not just the most double bonds, but the most conjugated double bonds, the ones that are involved in more resonance. Okay? So that's kind of our big lesson out of ultraviolet spectroscopy. Okay? Increase the conjugation causes an increase in lambda max. Okay? And that's because what ends up happening when you look at your pi system is that we end up having to jam more orbitals into the same space. Okay? And because of that, we start decreasing that gap between that HOMO and LUMO. Okay? Questions on that?
Yes.
Yes.
Is conjugation another, well, it's not the same thing as resonance, but,
Conjugation means you are allowed to do resonance. Okay? Without conjugation, you can't do resonance. So they aren't the same thing, but they are partnered with each other. Yeah.
Are triple bonds different, or?
Triple bonds are just pi bonds as well. So if we link a triple bond near another double bond in a conjugated system, that triple bond will still act, for all intents and purposes, like a double bond. Because what are we actually conjugating? We're not conjugating double and triple bonds. We're conjugating pi bonds. Okay? So when we're looking at our bonds, it's no longer single, double, triple, because that's pretty useless. What we're looking at is sigma and pi. Those pi orbitals, those pi electrons, are higher in energy, which means we can start to do different things with them. One of those things is looking at UV Vis spectroscopy. So increase conjugation, increase lambda max. Decrease conjugation, you decrease lambda max. Okay. Questions? Okay. Pretty sure that's all I got on UV Vis. It's not a whole lot. Okay. Where it becomes in handy is you're looking at colored objects. That actually kind of gets fun. Oh, my screen has not changed. That's fun. So I'm going to talk about what you're seeing up on the board. In theory, my computer will catch up here in a second. The IR region, what's happening in the IR is that you're looking at typical ranges for your wavelengths with these 10 to the minus 4 centimeters. Those values end up being so large that we don't really want to go through and use, why did I just blank? Wavelengths. We end up shifting into something known as wave numbers, which is, for all intents and purposes, the same thing. Okay? Sort of. The same thing as frequency. Your wave number is 1 over your wavelength. Okay? Over your wavelength, I believe. Okay? You can do some calculations if you want, but it's not all that important. What you're going to be ultimately responsible for is that you're looking at a slightly different range. That range is now going to be referred to, since it's nicely covered up in my slides, and the computer's dying on me.